Hello, this is the second lecture on quantum gravity. Welcome. I was yesterday introducing the subject, why one is interested, and I gave some very rough preview of some particular features of gravity that necessitate a special treatment in the quantum theory. So one way this search for a theory of quantum gravity can be phrased is to say we're looking for a quantum dynamical principle, kind of a quantum analog of the Einstein equations, which we then will, proceed to solve, and that solution should give us kind of a quantum analog of what is a solution to the classical equation, which is, of course, a curved spacetime. So one would expect that in the quantum series, this would be kind of a quantum spacetimes which say something about the structure and dynamics of spacetime, including the very shortest scales. And I also introduced the Planck scale for you. And of course, in the end, one's aim is to make some novel predictions to at least directly or indirectly verify whatever theory one has come up with. Now, I also briefly said something about the universality of gravity, and this, amongst other things, also motivates why your average theoretical physicist, well, let's say a person who has thought about high energy, typically thinks there ought to be something like a theory of quantum gravity, although, well, maybe it doesn't have too many practical consequences right now, but simply in order to complete the theoretical picture we have of the four fundamental interactions. Ever so often, the argument comes back, oh, maybe we can get away, even as a matter of principle, not just of practice, without quantizing gravity. Maybe there is, although there are quantum theories, all our fundamental interactions are at the most fundamental level quantum theories as we currently understand them. Maybe that is not true for gravity. Now, there again, rather than saying, okay, maybe it could be like this, well, there's also something you have to show. Why should it be like this? So it's not that this is an easy way out. It's certainly a minority opinion, and it's not what is suggested really by everything we know currently about physics. As that, looking back at what we've learned in the 20th century. I also mentioned to you that, of course, the weakness of gravity is something that permeates and makes difficult our search for a theory. Of course, on the one hand, well, primarily because any observable effects are just so tiny, and the Planck scale itself is just so tiny, so small that we are many, many orders of magnitude away from probing it directly with anything like a particle accelerator. Okay, now what we are embarking on today is getting a better idea of the degrees of freedom, the physical degrees of freedom that are described by the gravitational field. And in part, this will be a recap of something you've presumably already looked at in your relativity course, of course, and in part, it is preparing us for, well, how on earth do we quantize this theory? So, of course, it's best to understand now what you have given classically, because, as I also emphasized yesterday, that is something you will have to rederive from any quantum theory. In particular, of course, it will have to contain, at appropriate scales, the information that's given in the classical theory already. So we get started on kind of a covariant way of thinking about things. That means one works with space-time quantities, so the metric g mu nu. And one interesting thing one immediately focuses on are particular classical solutions to the Einstein equations, which are given by weak gravitational waves. Now, a technical definition, and we'll get to the details later, would be to say it's a linearized approximation. So it's an approximation in which I can solve the Einstein equations, and it describes kind of wave-like excitations of the classical field. rather analogous to wave-like solutions you find, say, for the electromagnetic field. So it's kind of deformations of space-time, kind of ripples in space-time that propagate through space-time. And why are they very important? If you want to think about quantum theory, well, for once, if you start studying relativistic quantum field theory, say you look at a simple bosonic scalar field, then of course the way to do it, you will start kind of quantizing the free field theory. And what are classically the solutions to the free field theory? Well, they're wave solutions, which you can superpose to get new solutions. So they are standard solutions which are just solutions of the wave equation, which you can just immediately write down. You can write down immediately a complete set of those. And for instance, when you then start building up perturbation theory, of course, you are referring very much to these solutions and then kind of systematically build up interactions on the basis of this state space. Now, so it's the starting point of a perturbative quantization. And of course, kind of in analogy with what one would expect kind of from, say, QED, is that the fundamental excitations, these wave-like excitations, are kind of the carrier of the force field. And so that in QED, of course, that would be the photon, that, so where I'm thinking that electromagnetic interactions are just carried by these propagating photons. And similarly, here, the question arises, well, do I have something similar for gravity? Can I also kind of identify particle-like excitations that I then think of as the carriers of the gravitational forces? And as we'll see, formally, for weak fields, that's exactly the picture that arises also for gravity. So I'll be rather brief, but some of these things will be just reminders of stuff you already know. So now, so these are, as I said, let me write a few things down. These are linearized excitations. Of the gravitational field. And they form the starting point of kind of a standard perturbative quantization, quantum field theoretic quantization of gravity. And kind of these the carrier particles of this interaction. So let me write hypothetical or theoretical. And these are massless kind of spin 2 particles. Well, I'm saying hypothetical because we haven't observed any single gravitons. That's a question I'll discuss a little more later. So this is just kind of in analogy. So general relativity, the classical theory of Einstein, predicts that such solutions exist. Now, first of all, how does this differ from the Newtonian theory? Well, in the Newtonian theory, gravitational interactions are instantaneous. Well, of course, these wave solutions are not instantaneous. They are things that just propagate at the speed of light through space. So they have a very large but finite speed. And this type of solution simply is not described by Newton's theory. So it's a new thing, you'd say, in general relativity. And how do they come about? They come about if you have a kind of heavy mass that is accelerated. So a stationary object won't, say a spherical object, won't generate any gravitational waves, but a moving object will. And there are, of course, in our own universe, examples of such sources of gravitational waves. Again, I should maybe say theoretical or hypothetical sources, because we currently still haven't detected directly any gravitational waves on Earth, despite the fact that very, very sensitive gravitational wave detectors have been built for, or have been even operational for considerable time. Now, the problem is again that the signals are extremely weak. So again, the weakness of gravity comes into play here. Everyone believes that these gravitational waves are there, because otherwise there's something fundamentally we've not understood about Einstein's theory, or Einstein got it wrong, or partially wrong at least. So that would be extremely surprising. Nevertheless, kind of these gravitational wave detection is, one of these things that are always 7 years away. You ask someone, they said, "Oh, when will it be detected?" They say, "Oh, yeah, well, we are very optimistic, but it's time, it's time translation invariant statements." And it's of course not helped by the fact, there are, well, what are the detectors? What are they like? There are laser interferometers. So where you have a light ray just being passed between mirrors. So you are you can very sensitively detect kind of tiny deviations in the length, say, of the arm of your interferometer. So they are ground-based, while the current ones that exist are ground-based. So you might have heard about LIGO and Virgo. And the thing is that to detect a typical signal, say, coming from a binary star, you need to be able to pick up a signal at least, with an accuracy of 1 part in 10 to the 20. And in addition, you need to know what you're looking for, kind of what type of signal you're looking for. So, and our detectors, the ones that are currently in operation, they are just, at that borderline, but they haven't seen anything, and they're now being updated. There's also, you might have heard about LISA, so that is was to be a space-based gravitational wave detector, and unfortunately NASA has recently pulled out of this operation. So I hear now it's going to be called ELISA, where E, I don't know, maybe stands for European, because ESA is still putting money in this. So that's an ongoing story, a slide aside. So this type of solutions was first noted by Einstein himself back in 1916. But already then he realized, well, he then thought, well, these signals are so weak that they're never going to be detected. Well, so far he's been right, but hopefully not for much longer. Now, so they're very weak. And so if I, how can I generate a gravitational wave? Well, I just I accelerate some mass. So if I do this, for example, of course, it doesn't become an appreciable wave of any appreciable strength. So you really have to go to very, very massive and rapidly kind of, for example, rotating stars. And although there hasn't been direct evidence for gravitational waves, there has been indirect evidence. So there's this very famous PIRSA binary system, the House-Taylor binary, whose energy loss one has kind of observed indirectly by kind of looking at how its orbital velocity changes over time, and compared to calculations you do in Einstein's theory about how big this effect should be, and they agreed to within a fraction of a percent. And that's, of course, what a Nobel Prize was given to House and Taylor for this. So it's strong evidence that indeed gravitational waves exist. Of course, they carry energy. So if you have a system like that, it radiates as gravitational radiation, and the system loses energy in a specific way, which apparently quantitatively, at least for systems we know, is very well described by Einstein's theory. Now, so what we detect, of course, in the vicinity of, say, such a binary, these are strong waves. So, and they're associated with a lot of energy, power, whatever, 10 to the 25 watts or something. Now, when they reach here, of course, they are very, very weak. So this weak gravitational waves, this approximation we'll be using, is actually an excellent approximation to describe them the way they reach us here. Of course, people also try to understand dynamics, the kind of the non-linear classical dynamics of these binary systems. And this you can try and do with numerical means. So people try and succeed to a considerable degree in modeling, say, binary systems, where two, say, neutron stars circle around each other, to model these numerically and try to extract kind of the precise form of the gravitational wave signal that these will emit. Because this is also an input, that is needed to understand, well, what frequency do I have to look at? I mean, it's the very simplest thing. What kind of waveforms do the particular sources emit? Right, so this is all information that's needed. So it's all classical, but of course highly non-trivial because of these non-linearities. Now, what does this gravitational? So the weak gravitational wave. What kind of approximation is involved at the level of the dynamical field of the theory? Well, call this G mu nu of x. So this is the 4x4 symmetric Lorentzian metric. So we decompose that into a piece that is the Minkowski metric plus, well, a perturbation. So this is, of course, in kind of Cartesian coordinates, you might say, which we'll be using here. This is, of course, a trivial metric, diagonal constant metric. Now, the weak field approximation would consist in assuming that this perturbation is very, very small, just numerically. So the modulus of all of these is much, much smaller than 1. Of course, 1 is the size of the entries of that matrix. Now, there is, in order, so what one wants to understand here for this particularly simple case of this weak field approximation is, now, where is the physics in these fields? So I already mentioned yesterday to you, there is a big redundancy in the description of these G mu nu of x's, because they will change their explicit functional form when I make a coordinate transformation. Without that, resulting in any measurable, physical effects. So they're kind of gauge artifacts. And of course, this field F mu nu of x will carry the same type of redundancy. Okay, so the question is then, can I identify in this simple case of linearized gravitational waves, kind of where in this set of a priori kind of 16 numbers, leaving, well, not accounting for the symmetry of those, where are kind of the 2 degrees of freedom of the gravitational field? And it's particularly easy to see it on the field space of the F mu nus. So the fact that we have a redundancy, it has many consequences, but one way, one expression this finds is that I am allowed to put additional conditions on these F mu nus, so constraining conditions, without losing any physical degrees of freedom. And these are so-called gauge conditions. So, and a gauge condition that is very suitable to dealing with these gravitational waves is a so-called harmonic gauge. So, what is it? It's also called the de Donda gauge or the Lorentz gauge. These are all the same things. And they impose an additional condition on these F of the form partial del nu F mu nu minus 1/2 del mu F nu equals 0. And here I'm using not covariant derivatives, but, well, it's already kind of tailored to an expansion. So I'm using the fact that this acts like a kind of background metric, and to the approximation I'm working with, I can just substitute the covariant by the normal derivative. Yeah?
You said that if you have only 2
Yeah, these are many more. Yeah, so these are, taking into account the symmetries, this is a matrix with 10 entries. Okay, but what I'm saying is most of these are redundant. So you know,
So why do we have only 2 degrees of freedom?
well, I get to that. So the easiest way to understand what these 2 degrees of freedom are is actually in this weak field approximation. So they turn out to be the polarization degrees of freedom of waves that move at the speed of light. So similar to photons, you see. So you have kind of transverse traces degrees of freedom, but this is exactly what I'll be getting at with this construction. So it exhibits exactly kind of the answer to your question. Okay, now, if you substitute this decomposition into the Einstein-Hilbert equation, which we had on the board yesterday, then the following happens. So substituting this Ansatz star into the Einstein-Hilbert equations, where I'm now I'm not including a cosmological constant term just for simplicity. Let's assume, well, it is small, of course, in reality, equal to 8 pi gn t mu nu. What do I get? Now, in the first place, let me just substitute in this decomposition without the additional assumption that these things are small. Okay, so this is just, if you like, a redefinition of variables. I've translated the metric variables just by a constant shift given by this Minkowski constant term. Right? But otherwise, I mean, nothing significant has happened. Now, when I substitute this in there, using this harmonic gauge condition, already using that, then I get the following. So this is a D'Alembert operator, the wave operator. So this is a D'Alembert associated with the Minkowski metric, eta mu nu. And then I get a right-hand side, which is minus 16 pi g Newton t mu nu minus 1/2 eta mu nu t plus something I call curly t mu nu, depending on f and derivatives of f, bracket closed, where this t here is by definition the trace, again with respect, of the energy momentum tensor t mu nu with respect to the metric eta. So this is I have to emphasize, it's an exact equation, right, where I've just decided to zoom in on particular terms, like this here, kind of box f mu nu. I'll leave this on the left-hand side and throw the rest to the right-hand side. Now, this is kind of fairly clear. This just comes from here in a straightforward way. Now, what I've lumped together here is kind of all the rest. And it's, in particular, it's all contributions that are of higher than linear order in the f mu nus. Okay? So it's all what sits in here. So this is kind of the nonlinear piece. With respect to the dependence on f. And, you know, what linearized gravity is to ignore everything that's beyond linear order in f, which means setting this to 0. That is kind of then the weak field approximation to lowest order. Okay? And that is then the equation one would try and solve. Now, so, and of course, if this is not there, and then say, if I don't even have any external sources, then this and that will also be 0, then this is just a simple wave equation. And, well, we should all be able, you know, to solve that and find a complete set of solutions. to z, depending on, of course, boundary conditions. Now, the full problem is, of course, much, much harder. This is nonlinear. And you see kind of the appearance of these f terms on the right-hand side, f-dependent terms, means that, usually, the way we read the Einstein equations is geometry equals matter content. Now, the way I've written it here suggests, well, the metric and its derivative give themselves a contribution to the source. So they are their own source. Another way of phrasing it is to say, well, gravity interacts with itself. Right? So you have here all these higher order terms that contribute if you go beyond the weak field approximation. And of course, it will make it very, very hard in general to solve this. Okay? So, but this is also something intrinsic. So there is self-interaction in the field. There are nonlinear terms if I write down the equations of motion. Now here I have written them down with a specific choice of fields. Because I'm anticipating, now I will kind of get rid of this here in the linear approximation. Yes?
So in those nonlinear terms, are they in a way to strengthen the wave, or are they kind of, will they diminish the wave after a while?
Well, that's not so easy to answer. That just depends, of course, on very much, well, how it will just not be, there will be deviations from the standard wave behavior. And in order to understand which way they go, then you go to the next order, maybe in the approximation. If you want to go slightly beyond the linear term. But otherwise, of course, you don't know a priori, right? So you don't even know whether you'll be able to find any analytic solution. So of course, you can already see that your life will be difficult, I would say, unless, again, there are maybe additional symmetry conditions you may impose in certain situations, which then makes this kind of this here manageable to some degree. But a priori, well, there will just not be linear waves. That's all. That's all I can say. So, okay. So linearized gravity is keeping this here. Linearized gravity is just this. So keep only terms which are at most linear in f mu nu. And of course, this is an approximation. And there may be situations where this is a good approximation, then, interesting physics you'll be able to extract from solving this equation, but it might not be it's of course not always a good approximation. Okay. So this right-hand side, of course, you can think of as some kind of effective energy momentum tensor, kind of including the effects of gravity themselves. Okay, now let's from now on, for the remainder of today, stick to this linearized, somewhat simpler case. Now it inherits a redundancy, so a gauge invariance from the full nonlinear theory. And more specifically, what is the transformation I can perform on the linearized fields F that leaves the physics invariant, or under which kind of solutions get mapped to physically equivalent solutions? It is the following. So the physics of this linearized gravity is, invariant under so-called infinitesimal diffeomorphisms. So of course, the diffeomorphism is a technical term for a usually smooth one-to-one map of the space-time onto itself. And it takes the form, if you are given a specific set of coordinates, it will get you from some coordinates x mu to some mu coordinates y mu, given by x mu plus xi mu of x. Where now for this linearized case, again, I'm demanding that these xi's should be small. One thing to note, of course, you might have come across gauge symmetries in various contexts. Here, this is a redundancy that's parameterized not by kind of global parameters, like something like Lorentz symmetry is characterized by, say, 6 global rotational boost parameters, but it's parameterized by functions, a whole function space. So it's a so-called a local invariance because my symmetry parameters themselves depend on x. Okay, so, and for any function or bunch of functions, x mu of x, I have such a symmetry. So it's a kind of function theoretic redundancy. And what happens to my fields f mu nu under such a transformation, or f mu nu gets transformed to some f tilde mu nu equal to f mu nu minus del mu psi nu minus del mu psi mu. And again, I presume probably you've seen things like that in your relativity course. Now, here, let me take the opportunity to say a little bit about kind of the physical situation one meets in the presence of such redundancy, which is, of course, true for many systems, also including, of course, gauge field theories. Yeah? So what I mentioned above here, that I can impose additional conditions on the fields without kind of loss of generality for the physics to be described, it's also known as making a choice of gauge conditions. And so one way of illustrating kind of what's going on in a geometric sense is the following. So, well, we can kind of fix a gauge to get rid of some of these degrees of freedom to exhibit kind of what I call kind of the true physical degrees of freedom. Of course, this is a little bit subtle because I have to choose kind of the condition just right. I mean, I have to choose sufficiently many conditions that really all the redundancy is eliminated. But I have to be careful not to impose too many conditions. Then I would start kind of without, with maybe unintentionally putting restrictions on the genuine physical degrees of freedom. So, what you want to do kind of is the following schematically. So let this be the space of all field configurations. Now, for gravity, this is, of course, is an infinite dimensional space, right? So of all, say, configurations G mu nu of x, running over a piece of space-time or even all of space-time. Yeah? Now, I have a redundancy, a gauge redundancy. That means I have an action of a certain, well, it's a group action, right, which creates so-called gauge orbits on this space. That means, I'm sitting here. Now, in this linearized case, I'm sitting here at some f mu nu. And now I've given you transformations of which I claim that if I impose them, if I apply them to an f mu nu, I get to a so-called gauge equivalent configuration that corresponds to the same physics. Yeah? So, and the picture here is that one would move under such a transformation along a so-called gauge orbit. So my f tilde mu nu is along here. And if I had chosen, you see, some other function xi, I would find myself somewhere else on this gauge orbit. But all points on the orbit are physically equivalent. Right? So there's no physics. I mean, there's no new geometry associated with moving along here. The explicit fields, they will look totally different. So if I look at the f tilde mu nu, I might not realize, at first that, well, I'm just talking about the f mu nu in disguise. It has just been kind of translated by a coordinate transformation, by a diffeomorphism. Now, what a gauge condition does, or ideally should do, of course, the whole space, well, modulo mathematical subtleties, which we'll not go into, is kind of falls into a bunch of such gauge orbits. So these gauge orbits, they're closed on themselves, right? If I really had a group action here, and I want to count. Ideally, I want only to pick exactly one configuration from each gauge orbit. Then I have eliminated all the redundancy. And doing this is the same as saying I choose a gauge condition. Now, finally, here is my chalk. So a gauge condition could be something like this. You see? It's just a line, that cuts each of the orbits once and only once. And then, well, all the physical degrees are still there. The gauge redundancy I've got rid of. So what a gauge condition like this harmonic gauge does is really kind of define some space, some are orthogonal to these gauge orbits. There are many, many ways of doing this. Often in a given physical situation, one choice will be much more convenient than other choices. But in principle, there are very many ways of doing it. And they should all lead in the end, to the same physics. Okay, but so that's the picture here. And these things, as I said, they are called gauge orbits. So, here one is moving along gauge orbits, but a gauge choice is perpendicular to those. So this here would be kind of a good gauge choice. So schematically, it's just some function of f equal to 0. I mean, without loss of generality, I can write any gauge condition like this. I mean, this is a very general way of writing it. Now, what would be an example of bad gauge choice? Do I have other colored chalk? Not sure. Okay, a tiny piece of green. So a bad gauge choice would be something like that. Some orbits are cut twice, or even more often. See? Or something that only cuts through some of the gauge orbits and leaves out others. So that misses out then on relevant degrees of freedom. So these would be examples of bad gauge choices. And for each such condition you give, you have to check carefully that it does just the right thing. So this is kind of bad gauge choice. All right. Now, what you do for kind of source-free linearized gravity, that means I have set T mu nu equal to 0. The equation I had up there becomes simply kind of the wave equation, box f mu nu equal to 0. So the homogeneous, so-called homogeneous wave equation. And now from your relativity lectures, or you should know that now the solutions here are plane waves. And for us, it's interesting. Let me make it completely explicit what they look like, kind of, as a 4x4 matrix. So without loss of generality, let me just pick one direction of propagation for the wave. So let's say that it have a wave vector. So it's a spatial part of the 4 vector, k, which is along the x direction. This is just unit vector in x direction, Minkowski space, and let k be equal to omega 0, 0. Then the corresponding f mu of x belonging to a plane wave solutions propagating in that particular direction has the following kind of linearized metric tensor, many zeros, 1, 2, 3, 4, 0, 0, 0. So it's only non-trivial in this bottom left-hand, right-hand corner, 2, 3, minus a 2, 2. So only those are non-vanishing, and you see they're just 2 real parameters, a22, which appears twice here, and a23, which also appears twice, times e to the I omega x minus t. So this is, of course, kind of I'm writing a complex wave, of course. You know, so I can always decompose it into its real pieces, but just for simplicity, let me write it in this usual complex form. So this is just the wave in the x direction, and this is its amplitude. Now, it's everywhere 0, apart from kind of the, this is x direction, apart from things that happen in the y-z plane. So these are exactly kind of the, if you like, the orientation of this field tensor of the metric. So, of course, I mean, the gravitational field G mu nu is a tensorial quantity. So it's a field, so it's not a scalar field like a single number, but it has kind of a directional properties associated with pairs of directions mu nu. Right? And so that's what happens for the gravitational wave. And so this is called a gravitational wave in transverse traceless gauge. That means, as a matter of fact, that in addition, it turns out, well, one uses this harmonic gauge, but that is not quite sufficient. One imposes some additional conditions and is then uniquely led to a parameterization of these arbitrary waves in terms of 2 parameters. And these are exactly the polarization degrees of a propagating gravitational wave. Yes?
I don't see why it should be tested.
No, you don't see. I haven't given you the derivation, but I'm just kind of stated that you can impose further gauge conditions. And these exactly restrict, without losing any physical reason, restrict kind of the explicit functional form of this f mu nu to be this. So it's a specific choice of coordinate system has been made, or I should say is possible, and it transforms the general solution to this form.
I mean, why if 2 equal the amplitude of f22 is equal minus the amplitude of f33? What's this? What physics behind this?
Yes, the physics behind this is that kind of we have here, without loss of generality, we've picked one of the directions. It could be any other direction. Now, for this one, so for a fixed wave vector k, we're asking ourselves, now, how many degrees of freedom can I have that are associated with the waves that propagate at the speed of light in this particular direction? And what I'm saying is the remaining freedom is parameterized by exactly 2 numbers, which are have to do, well, with the directions perpendicular to the axis of propagation. So this gives you directional information in the plane perpendicular to your actual wave propagation. So this is exactly kind of polarization degrees of freedom. I say a little bit more about it just in what follows right now, and that probably helps you to understand what I'm talking about. So that means here, the general solution solution kind of for a given wave vector has 2 free parameters. So each k mode, right? And of course I have an infinity of k modes, right? Because of course I have infinitely many degrees of freedom in the gravitational field. But each of these k modes has an additional 2 free parameters. So these are kind of the physical degrees of freedom. The physical degrees of freedom of linearized gravity. Now they have, as I said, a very specific and quite transparent physical interpretation. I expand on this a little bit more. If I had done this in a more general situation, I had analyzed now which of, away from the linearized skies, which of my degrees of freedom are actually physical, I would also have arrived at the number of 2, but it would have looked, it looks different. Of course, to make the degree of freedom counting precise, actually, one has to do something that's much more complicated technically. So one has to, the easiest way is to go to canonical formulation classically and make exactly, cleanly separate out physical degrees of freedom by a procedure that's called a Dirac constraint analysis. That's a topic we'll be looking at a little bit next week when we talk about canonical quantization. Okay, I was asked for a somewhat more physical picture of what is behind this. Now, let me read off from the form of this 4x4 matrix what are kind of the direction of the polarization. And the direction are, well, there are 2 tensors. There are a subset of symmetric 2x2 tensors are those that are transverse and traceless. So of course, if you are given such a matrix, then you can decompose it into subspaces of matrices which have satisfy additional constraint conditions. And here we'll be looking at kind of these polarization tensors. So unit linear polarization tensors. Now, reading them off, so I give them names. So these are specific 2 tensors. You can think of them as quadratic matrices, right? And I can invent, of course, a basis in the space of 2 tensors. And I'm just now picking out the 2 directions along which are relevant for the polarization of these waves. One, let me call it E hat plus. It's given by a tensor product, of course, of unit vectors minus Ez tensor Ez. You see, of course, any single direction, if I was just talking about vectors, had a basis consisting of, Ex, Ey, Ez, say in the 3 spatial directions. Now, if I'm looking at the basis of 2 tensors, of course, I have to take all pairs. And now I've picked out a linear combination of 2 of these pairs. And this is called kind of the plus polarization. And this is called the cross polarization. So it's a different linear combination. E. Y tensor Ez plus Ez tensor Ey. And you see, this, you can just read off, these are exactly the non-vanishing components of this wave in the x direction. They're along these two unit polarization tensors. So this is the cross polarization. Okay. Now, what is the physics behind this? Now, this is best illustrated by now considering, by putting oneself in the plane perpendicular to the propagation direction of the wave, so in three-dimensional space, right? And then placing an array of test masses or test particles in a circle. Yeah. So that's the idea. Try and draw a circle here. And now what you look for is the effect that a gravitational wave passing kind of through perpendicularly, now through the plane of the blackboard, would have on the relative locations of these test masses. And now it turns out that the gravitational wave will, well, change their relative position. It will kind of squeeze and extend this picture. So relatively speaking, so what will happen? So for example, if you look at E, what a plus polarized wave would do, it would change this pattern, of course, periodically with time. So looked at a little time later, for instance, we would find that it gets squeezed kind of in that direction. Then it goes back kind of to the original circle shape, the test masses, and a little time later, it will get squeezed in the perpendicular direction, like so. Okay, so I have these test masses, and now the wave is passing through, and they will now rhythmically kind of change their shape, etc. So, well, sorry, this has become a little smaller than I intended, but you get the hang of what I'm trying to say. Now, what would this other cross-polarization do? You find exactly the same picture rotated by 45 degrees. Okay, so then the circle gets just squeezed in this direction and that direction, kind of periodically. So this is just kind of the physical effect. And it's pretty straightforward, simply to do the computation given a linearized wave. What one has to be slightly careful about is one needs to work with kind of physical distances, not coordinate distances. But it's, this is kind of textbook GR stuff and very instructive. And that's kind of illustrates just the physics behind it. What happens? What happens when a gravitational wave passes through you? Well, you will also undergo, some slight, squeezing and stretching. It's very, very mild. But of course, if you, compute the forces that, say, would arise when you, fall toward a black hole or something, then these forces get very appreciable. So then, you're losing sight of part of your body in that direction or that direction very quickly. Okay, so this is the physics here. By taking linear combinations of those, so these are two independent solutions. Okay, now by looking, it's maybe immediately obvious, but by looking at an appropriate linear combination of those, I can, for instance, generate a circular polarization, where then the squeezing, will just kind of rotate around the left or the right. Okay, so let me just write this down here. So you get, sorry, what I wanted to say is here, by taking linear combinations, okay, one can obtain a unit kind of circular polarization. polarization with associated polarization tensors E hat R for right is 1 divided by square root 2 E plus I E cross, or the left circulating wave is exactly the same thing with a relative minus sign, minus I E x. And of course, for the physical waves, well, you look, of course, always at the real parts of such complex expressions. Now, one last thing that interests us has to do with a quantity that is called the helicity of a wave. And the helicity of a wave has to do with how a wave that is polarized in a certain way behaves under rotations in the plane of the polarization tensors, or vectors, or spinors you have. And that is, there are various possibilities how kind of the wave solution transforms. And they correspond to different physical properties this wave has, and also that distinguishes different types of radiation. For example, electromagnetic from gravitational. So that is just, this writes this down under as a last remark today. So what happens under a spatial rotation? In the YZ plane. So that's the plane where my polarization tensors live. First, the unit vectors transform, just by simple rotation in the YZ plane around some angle theta, like this. And EZ becomes EZ prime. Just a two-dimensional rotation matrix. I mean, extremely straightforward. Plus cosine theta EZ. Now, if I have the transformation rules for those, I can immediately figure out what the transformation rules for the tensors are. So these quadratic expressions. And what you find is the following, that kind of the right circularized polarization tensor transforms to the e to the minus 2I theta relative to its untransformed one, and you could almost guess it. So the left circularly polarized wave corresponds with exactly e to the in a negative, so e to the 2I theta times the original polarization tensor. So what you see is that kind of the identity is reached for theta equal to pi. Not 2 pi, as would be the case for a vector, but already after a pi rotation. And that's a property of a helicity 2 wave excitation. Okay. Now, if we had done this for electromagnetism, we would have found factors e to the plus minus I theta. So you would get back to the same after a rotation of 2 pi. And that is a helicity 1 particle. Not particles, sorry. We are still at waves. But what this will translate to, kind of in the quantum theory, will be spin, particles of a certain spin. So gravitational gravitons will be the spin 2 particles. So that goes back. That explains a statement I made right at the beginning of the lecture. A photon is a spin 1 particle. If you look at a neutrino, a neutrino is an object whose wave function picks up a factor -1 after I make a full rotation. And I have to make 2 rotations to get back to the identity. That's an example of a spin 1/2 excitation or particle. Okay, so let me just write this last thing down. So if a plane wave let me call it phi, just classical for the time being, transforms as phi going to the, with a phase factor e to the I h, sorry, theta phi under a rotation by theta by theta kind of around the axis of propagation. Of the wave. This h is called its helicity. So what we found here, h could be either plus or minus 2. And as I said, in the quantum series, this will then translate to the spin of the particle. But you see here, its origin in a specific property of the classical wave solutions. OK. Thank you very much.
Excuse me.
Yes?
When you do this conversion, you sign the exponential should be different opposites. Plus for r and not for n.
What do you mean here?
The sign in the exponential. Yeah. That should be called the depth and the
Which one? Well, this is certainly how it comes out if I use the linear combination I had on the blackboard. Don't be too worried if you. It just depends on the definition.
It was like this.
Because it depends on which way I look at the wave. If it comes to me, or if I look from kind of in the direction of the propagation. Yeah.
Wow.